Welcome to my channel, Science to Technology. In today's show, Computer Wednesday, we're going to talk about open source hardware. So let's dive right into it. Now, why do exactly we need open source hardware? We have open source software. Then why do we need, we also have open source architecture, aka instruction set architecture. But why do we need hardware? Well, reality is the world runs on what we call integrated circuit or ICs. Everything. At this point in time, you have to understand, whole world goes through cycles where some technology becomes the most important thing. For example, once we figured out internal combustion engine, oil became the next big thing. It was the black gold. After that, we had technology companies. After that, data became the next big thing. Right now, it's ICs because, well, what the hell you going to do with the data without processing it? So ICs is right now the core technology. And here's the deal. It's important for everything. Meaning your car will not work. As in, like, can we make car without ICs? Yes. Will it be as fuel efficient as or current one? No, just no. So if fuel efficiency is matters to you, you have to invest in some ICs. Now again, cars are a bit too overdone with ICs, but you have to do it. And not to mention, this affects everything. You may be like, oh, I don't get affected by it. No. Everything, single thing's affected by it. Like you can be, there are apparently only 3 countries that can make turbine blades of like high enough quality where it can make supersonic jets and all that jazz. Okay, cool, awesome. Russia is one of them. Cool, awesome. Here's the deal. They cannot make ICs. What does that mean? That simply means they will claim that we have this fighter jet and hulululu. But here's the deal. If Western world cuts off their IC supplies, they did. So you have to understand, from a national security point of view, it matters. From a company point of view, if a company cannot make a proper tool with proper ICs, for example, cars, let's say a new emission standards is introduced in the market that requires you to fine tune your engine ignition sequence, that requires better ICs. If you don't have that, you're dead. So it matters to everything. National, company, industry, whole industry runs on automation. All that automation is done by ICs. If you don't have that, if your country does not have enough supplies for that, your automations would be expensive. Consequence, outside world will like you flood your market with cheap imports, and then you're dead. Then it affects you and me also. So it is one of the most critical infrastructure technology that we have at this point in time. And only few companies know how to do this in modern times, flat out. Like back in the days, there were many companies that were trying, but with natural selection and all that jazz, only few companies have survived. Meaning we are literally, I'm not joking, not exaggerating, we are literally at the mercies of these gods, modern gods basically. So if ASML, somebody tomorrow decides, you know what, we're gonna charge some more to it. You may be like, oh, somebody can clone it. Trust me, people have tried, they cannot even come close to it. TSMC goes a little bit more profit. Nothing can be done. Like this is a company that is building ICs for military department. Again, radiation hardware, hardened hardware, because again, if you're going to space or things of that nature, you don't need nanometers, you need a bit more hardening. At that point in time, you may be using 200 or 400 nanometer. So we are literally, like, whole countries can be mercy of these sort of companies. Like, that's how serious these things are. These are modern gods. Like back in the days, oil companies were that, then it became the tech companies, then it became the data vendors. Right now, it's the IC guys. So what is the problem? Like, if it is this important, I cannot be the only one who's like, whoa, this is important. It's like everybody understands it, but here's the deal. The modern IC is idiotically complex, meaning the complexity of modern ICs is beyond human brain's ability to make it. I'm like, wait a minute, if human mind cannot understand how the heck human mind made it, well, it's not made by one human mind. Even one single processor is not made by one mind. It's made by a combination of hundreds or sometimes even thousands of mind. So fundamentally, it's beyond complex, meaning even if you give China, it's like, hey, this is epic process, they can like take it and like, grind it off and electron scan everything, they still will not have the ability to reverse engineer. Modern technologies is almost black magic. You cannot replicate it that easily. So how do we actually build it? Well, we use what we call multi-layer toolings. Now, again, it's not called that, it's just the logic of things. So multi-layer tooling allows you to automate multiple tasks. For example, you will say, give me the logic and or gate. The computer algorithm in the background will figure out which basically which transistor, which circuitry has to be designed for that. Then you will have multiple logic blocks added. Then somebody above you will design a system where you have multiple logic blocks added to do a specific function, be it encryption, be it decoding, whatever have you. Then somebody above it will design the whole sub-architecture where it's like, and then people below it is like, okay, that person is doing whatever the heck he wants, but I have to make sure that it fits inside the silicon manufacturing technology. If it's not the manufacturer, what's the point? Like it happens now when you can design anything in CAD software, but the moment you send it to a manufacturer is like, bro, this guy is high. Like it's not gonna be done. So you have to understand, like, it's not a single layer thing, and it's idiotically complex and many layers are there. And People can only master a small slice of that pie. Like if the slice is 100 slices long, only one can be handled by one person. Like, and you need best of the best of the best of the people. Trust me, when I say this, these are like on a level of technology that is needed to even understand it, it's on a whole different level. Like think about this, like we have processors that have billions of transistors. I would not be surprised if somebody tomorrow is like writes, oh, we have actually one transistor that exceeds 1 trillion transistors. Let that sink in. Like how the heck when you try to connect 1 trillion things, you can't. You just hope like everybody in the stack is working properly. The person who's designing the above thing, the person who's designing middle thing, and bottom thing, below bottom things, even bottom thing, core physical level, they are all working their best job. So you have logic units that you are adding, hoping that it works. That's why, like fundamentally speaking, you may be surprised sometimes, like how the heck Intel had like this sort of security vulnerability. Again, so many stacks has that sort of potential. And EDS, basically electronic design aid, this sort of softwares have proprietary tool libraries. Now, EDS software is available, like you can find an online one and all that jazz. That's not that big of a deal. However, those EDS are 100% useless if you want to make a silicon chip out of it. The reason for that is they do not have proprietary tool library. What are these proprietary tool libraries? Well, these tool libraries are developed by fabricators, meaning, for example, TSMC, Samsung, Intel, all of them will figure out like this is my manufacturing machine, this is what it can make. Okay, cool. How the heck you collaborate between the designer and the people who are actually making like CNC machine and CAD? How the heck you make that? There is an in-between layer. These are like Synopsys, Cadence. These are the layer management tools, so to say. They are the one developing the EDA libraries. So what they do, they actually have their own back and forth with the fabricators. Like, hey, I think we can design this logic architecture. This will be used multiple times. So like, let's say IO blocks, let's say basic encryption block, all those things. They will design it, like this company will design it, send it to fabricator. Then they'll have back and forth. It's like, hey, dude, I think you should not have this many vias at this location densities. Like they will figure out the fine tune. That will create the library. They will license that library to big boys. Those big boys will use those license algorithms and packages to build their ICs. There's a lot of layering in this. And before you even reach a point where you have an idea to actual physical silicon, you have to sign whole lot of NDAs. And these companies are big enough, big boys enough, and they have deep enough pocket that Intel would not try to cross them. Let that sink in. Like this, that's how deep their pockets are. You may never heard of these sort of companies, but that's the whole point. They have few people and they are great at what they do. There were used to be far more companies than this, but again, most of them died out. So problem is, right now, if anybody actually wants to do it, just remove the money side. Just the NDA side will require a whole team of lawyers just to go through it's like what they are actually signing off. So the problems are exponential at this point in time. And that's why our silicon technology is not becoming cheaper. Like each processor is becoming more expensive than the old one. Back in the days, we had like processor, then it started to become cheaper. Now it's going back up. Why the heck is going back up? It's because of all these layers that we have to deal with. The complexity of the design exceeded human brain's ability at this point. So you need hundreds of humans. Collaborating between hundreds of humans and hundreds of design rules, regulations, and all that jazz. Yeah, that's the problem. And NDAs, that itself is a problem. Then proprietary tool, that itself is a problem. So all that makes it idiotically complex. That's why no Tom, Dick, and Harry can just like, even China cannot be just like, hey, we're gonna look your processor, we're gonna clone it. Yeah, that's not how it works. They tried it, that's not how it works. These people are like, bitch, try, please, come on, try. So what's the solution of this? Well, solution is basically everything has to start from fresh. Now, thankfully, we have learned a lot in the past. So we can actually do that. For example, you have to make sure that you do not have any patentry, otherwise the lawyers will come. So you have to start with ISA, instruction set architecture. Thankfully, we have an architecture known as RISC-V. So RISC-V is like a language, but here's the deal. What's the use of a language if you cannot mass print a book from it? So like, for example, like you have this language, you send it to a printer is like, I'm not going to print it. Then what the hell? That's the same thing. ISA, if you have ISA, let's say x86, you have ARM architecture, or you have RISC-V, it's useless if you cannot manufacture the damn thing. So ISA have to be the first point of start, where it's like, okay, we have ISA, we can build something with it. Then you go to EDA, like the people who are actually making the software. Then at EDA have to have libraries from people who are actually manufacturing it. So Google is partnering with some big boys like Global Foundries and Skywater. Now, if you have never heard of them, they are not very big boys. They are big boys, but not very big boys. They have like other contracts like defense industry and all that jazz, satellites and all that jazz. But they are not making on 5 nanometers and all that. Like, for example, again, They can reach that, but their market is not there. So they are offering the knowledge that they have acquired for 180 nanometer and 130 nanometer. Now, without these companies' actual knowledge of how to actually manufacture, even Google cannot do it. That's why Google had to partnership with that. They cannot just like, oh, we're gonna make a branch. It does not work that way. You have to have some engineer who actually build this. Now you're like, isn't 130 nanometer and 180 nanometer useless? Well, hell no. This is too small for Mars missions. Current Mars missions generally use 200 nanometers. So this is actually cutting edge from NASA's point of view. And again, the bigger the gates, quote unquote, the harder it is for any cosmic ray to flip it, meaning your program can become a bit more of what we call radiation hardened. So and many times military also loves this sort of, because if ICBM is going above the atmosphere, it can be affected by radiation. So you have to design in such a way. So this sort of technology is not useless. And be mindful, while today we may look at, oh, these numbers are huge, we are going to a point where we have like, let's say 100, we have like 10 nanometers or 5 nanometers. But here's the deal, this is only 20 years ago. And be mindful, 20 years ago we had computers. We had majority of modern world was built 20 years ago. We are just exploiting it now. Like, you can build surprisingly large amount of things. And not to mention, let's say you are building a microwave. Do you really need a 6 nanometer processor in that? No. If 130, if that's cheaper, you're like, just shut up and take my money. That's why like Arduinos are not running on 5 nanometers and all that jazz. You don't need it. So they have to start with very basic, and they have to make sure it's patent free. For that reason, nobody is going to give their latest and greatest. You have to start with background. Then you have to have a lot of interplay between the people who are working in the fabrication lab and the people who are designing the ETAs, meaning this is the flow chart of this sort of system, and you need to create what we call GDSII files that actually goes to the fabricator, and then they fabricate the thing. Is complex, and you can see how many steps it has, but it has to be done that way. And without some big boys like Google and Skywater and Global Foundries, it cannot be done. And Google is the one that knows how to manage software, so they are creating a whole pipeline. Open, like GitHub has the software pipeline, like the Open Road project, Open Lane Architecture Systems. So support from giants are needed. It's not one of those things where like RISC-V was literally created by college professor. This can be done that way, but it will be like 500 nanometer. Like you can see that in a microscope. I have seen some YouTuber do that. I'm not even joking, like actual silicon fabrication using microscope. But again, nanometers are very small, huge. So it will be a very slow and methodical process, meaning we'll start with this, then brick by brick. Once we figured out how to use 180 nanometer, 130 nanometer, then we'll start to go down. Then brick by brick, we'll go down to, let's say, 50 nanometers. It's not going to happen overnight. It's going to take its time, and the whole software stack has to be fine-tuned, refined. Again, many things can be done today, but do not expect to, like, bit slap NVIDIA or bit slap Intel. That's not going to happen. So what is the aim with this? Well, Google is very realistic about this, and it's kind of, Google is playing it very wisely. They're not just like, oh lol, I want to make money. They're like, no, I want to plant some seed that's going to give a lot of other people a lot of fruits, but it's going to make me boatload of money for free. Like, again, that's the contrast. Like, they may be spending billions of dollars to get this partnership. They're going to make trillions of dollars in the future recuperating, right? So it's like win-win for all of them. So they have very realistic expectation. It's not pie in the sky. They're not like flat out. It's not designed for latest and greatest. It's designed for getting the things going. Like RISC-V, nobody's going to say that RISC-V is going to beat ARM architecture. Nobody's going to say it's going to beat x86, but it's going to be a fresh start. And many times when you have fresh start, that's more than good enough. Like, hey, I want to start something from scratch. I want to learn. I want to grow. I want to design something that does not require 500 layers of NDA. You want to start that. Good. So what Google is aiming for is easy to use, not the next big thing. Let that be very clear. Easy to use, meaning college students can sit down and actually design this puppy. What is this? This is a encoding chip for AV1. AV1 is another open source video encoding system, which was built again, supported by Google. So this sort of silicon, again, this sort of technology goes into everything, basically your dash cam, security cameras, your basically DVD player, Blu-ray players. Again, this sort of similar ASICs, what you call application specific integrated circuit, goes into all the things that decode and encode videos without consuming too much power. Again, this is the background of technology, but right now, if you wanted to buy a chip from, let's say, x86, not x86, as in like H256, H256 is a paid system, so that will cost you a lot of money. And not to mention, anybody who is actually building a tool for that, they're gonna charge you arm and a kidney for it. So fundamentally, you have to use everything open source. This is a very good example of that. Like AV1, modern technology. You may be like, oh, it's designed for like 130 nanometer. Again, it's still more than good enough. If you are a, let's say, manufacturer of security cameras, you have to create a feed where you're taking the sensor data and collapsing it into actual useful video format. This chip If somebody's gonna like this chip coming from any other major vendor will cost you arm and a leg, and you will require ludicrously large amount of bulk order. Another small startup can like deliver you this. Why they could not have done that? But nobody was building the software toolkit. Without that software toolkit, this is not feasible to do. But with software toolkit, college student can do that. So that's the idea. From idea to IC to become as efficient as easy as possible. They're not going for the latest and greatest. Can Apple make something similar? Yes, obviously. Can Google make something similar? Oh, yes, obviously. But again, both of them will pay far more. This is a college project. So that's the whole point. The old node will be only used for getting started, like getting the things going, making ASICs, making low power equipments, making some modern future technology that we have not even thought of. That's how it begins. Like Linux in the back end of this, it was a tool that people were trolling around with. But nowadays, it's a backbone of entirety of internet. So that's the same thing going on here. You may be like, oh, 130 minutes, does not matter. It's like a cool thing from start to finish, meaning you can build a whole computer processor using RISC-V, using this and all that jazz, and still get modern technology. Of course, the performance will no longer be close to like, performance per watt that modern system get, but you will be close and you will not have to spend billions of dollars on your lawyers. So that means a lot. And it's going to be a slow and methodic process, brick by brick. Basically, Apple Mac had G5, I think, had the processor that had the same node that these companies are offering to Google. So aim is very realistic. They are not aiming like, pie in the sky. And it is a very significant step because Google knows for a fact that they are the largest data collector. They need idiotically large amount of ICs to process at that. If they can save money on each IC, even by a little factor, in the grand scheme of things, that will be like just this whole investment from Google side will be like, dude, that's chump change. So what we can expect in the future? Well, Google funding a lot. Google is funding a lot, meaning they are pouring a lot of money into this. And they will benefit from it. Let that be very clear. They will benefit from it. But it will be beneficial for all of us, meaning if giant companies like Red Hat is working their ass off, let's say NASA is working their ass off on Linux, does not mean only NASA benefits from it, only Red Hat benefits from it. We all benefit from it. So that's the whole point. And open source also turbocharges education. That's really desirable. For example, instead of making some mock technology, imagine your let's say a badge actually designed a chip, a basic chip, let's say just a basic thing, reading time from GPS data, and that's it. It's like Casios have this technology. Many of the Casios G-Shock watches have the technology to use GPS to extract time data. Again, proprietary technology is super expensive. What if you figured it out? Again, it can be done, physics is there, but again, the software toolkit needed to develop that IC is just not there. But right now, it's there. What if they developed it and it's like, boom, every watch nowadays have GPS clock. So many things can be done in education sector. And imagine a country like India, which has so much engineering college, so much potential. If all of them even had like small sectors, and grand total there was a Indian body that is like observing everything, it's like, bro, we are gonna make a system on chip. So you guys work on encryption, you guys network communication, you guys VoIP protocols, so all these protocols, this. We can literally have a SOC in next 2-3 years. So that matters a lot. The turbocharging of education, shut up and take my money, just for that part, education part. And more brain side of problems gives you more option. This is one critical aspect. There is no such thing as in engineering where it's like, the perfect option. There, it does not exist. Meaning you will have variables which you have to control and manage. For example, how much money you want to spend to build it. That's the one thing. How much energy you are willing to invest on it. For example, let's say you want to build something that is running on battery power. Energy efficiency is far more important compared to somebody who's building a security camera and they're like, dude, we are running the security camera on PoE. They're like, we have the power budget. We would like our chip to be far more cost effective rather than power efficient. You always have to balance things out. So how do we create balancing? More people work on it. So more people working on, more brains working on, more colleges, more education system working on it, that will yield far more options. Then you can even select chips. It's like, hey, for my dash cam, I think I really need high speed. It's like for fast car, I need high speed. So they're like, dude, don't go with this AV1 encoder, go with this AV1 extreme encoders that is like specifically designed for 120 FPS. You can do that. A lot of brain power equals a lot of options. And it's everybody's interest, meaning it's not like, oh, Google is working on that, Google is going to suffer. No, they're going to make money. Let's say, like, for example, RISC-V is a very good example. So many companies are like, this is 65 plus members at this point in time. It has like Indian Institute of Technology, IIT in India is working on that. And basically every Tom, Dick and Harry company is working on it, like Google, Samsung, basically, which are, NVIDIA is there, Microsoft is there, DARPA is there, Menalox Technology is there, Micron is there, IBM is there, every Tom, Dick and Harry. This is just that AV1 open source video encoding system. Everyone is there. So that's the whole point. People have figured it out the hard way that it's far more efficient to build open source than to close source their technology. Some technologies, again, do deserve to be closed source, for example, encryption systems, but most of the time open sourcing things benefits us all. Like, can you imagine a world without VLC? Even they are like, you know what, this is awesome. AV1 encoding they want to have into it. Netflix is like, hey, having a system where we do not have to pay a boatload of money to a consortium that is charging for their codecs. Save up. So future is amazing, and I'm really happy that more and more this companies that are quote unquote evil, they are actually trying to be like, hey, you enjoy some benefits, we're gonna enjoy some benefit. Of course, we're gonna benefit exponentially more, but you're not gonna be left behind. So I'm happy with that. This is a good approach that world is moving towards, and more countries can actually build fabrication lab. Maybe not the latest yet, but maybe enough. They're like, dude, at least our cars, our core technologies, our main infrastructure technology is built in house rather than relying on TSMC. So future is good with this regard. I really like the approach of Google. So this was my presentation on basically open source hardware architecture. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.